All right, now that we have understood what the second law of thermodynamics means now and the meaning of entropy, now let's use the second law of thermodynamics in some of the practical applications. The first extremely simple idea is the combination of the first and the second law. Now we have very well known by now, we have seen this many times, the first law now. So dE is equal to del Q minus del W, and this being the second law is ds is dQ by T. Now if we want to combine these, we just would like to replace the dQ by T delta S. So dE becomes T ds minus del W. Now W, if this is PV work, we can write this as P delta V. Okay. Now this becomes dE T del S minus P dV. Now this is the combined equation for the first and the second law. This I'll name as equation 54 and this as equation 55. Okay. Now this equation can then be used as a fundamental equation to calculate the entropy change for a reversible process. Okay. So this was for the reversible process. Now this equation that we derived can also be used to get the entropy changes for irreversible processes too. Like we know how this can be used to get the entropy change for a reversible, but what Clausius and what the people who came up with this idea of the combined first and second law also said is that not only you can get this to get the delta S for a reversible process, you can also use this equation to calculate the value of the entropy change in an irreversible process. Now, how is this possible? Because how can you use it to do for the real equations? Now, the real equations are irreversible, right? They are irreversible processes. Now, S is a state function, right? S is a state function, and this is path independent. Now, the reversible processes we saw that can only go for exchanges in the entropy. So the reversible processes cannot produce any new kind of entropy. But now if in any process that is producing a new entropy, like it is not just exchanging, it is producing new entropy, that is an irreversible process. Now if this equation tells you that any amount of delta S ds is being produced, that means it is being produced by irreversible processes, real processes. Therefore, this equation can also be helpful to finding out the ds in real equations, right? Because in only irreversible real processes you are able to produce any new kind of entropy. So if this says that you are producing new kind of entropy, that means you are able to use it in real equations, right? Okay. Now let's see some basic types of processes, like we saw adiabatic and isothermal and isobaric, all these kind of processes when we were discussing the first law of thermodynamics. Now let's use the same concept. Now using this new law, we'll try, and the old understanding of the different processes, we'll be trying to find out the entropy change in different kinds of processes, right? Okay. So starting off, let's go for the entropy changing during a reversible adiabatic process. So whenever you say it's an adiabatic process, the del Q automatically becomes 0 by definition. Okay, so when this becomes 0, ds also becomes 0 Why? Because del Q in here becomes 0, so ds is 0. So in an adiabatic process, the entropy doesn't change. Okay? So in a process in which you don't have a change in entropy, that process is called an isentropic process. In which ds is 0. Okay? Please keep in mind that this means that there is no change in entropy. That doesn't mean that the system itself doesn't have entropy. The system has entropy. But when you were doing this process, when the system was undergoing this process, was doing this adiabatic process, there was no change in entropy. That's the idea of an isentropic process. Please understand that this doesn't mean that system has no entropy. The system has an entropy. This means that there was no change in the entropy of the system. Okay? All right. Now, moving on to a reversible isothermal process. So we now know that for what it means to be an isothermic process is delta T is 0. This means delta E is also 0. So in this equation, delta E, when this equation, in this equation dE becomes 0, then for a reversible isothermal process, TdS becomes equals to PdV, right? So we can write TdS becomes equal to PdV. Now our motive is to find out the entropy change, right? So we'll take the temperature to the other side, or we can just integrate it in here. Okay, so let's try and integrate this from, say, the entropy went from SA to SB. We have a TdS, and the volume went from VA to VB. We have a PdV. Now you can also take this temperature out, right, because this is an isothermal process. What this will do is this will integrate the S. So this will become a delta S. So delta S is basically SB minus SA. Okay, so I'm just writing it delta S in here for simplicity, and delta S is basically SB minus SA. Now you keep in mind that there is a T in here, okay, because this T came out, this was an isothermal process. And we have done this many times now. So PdV basically turns out to be NR. So P becomes PV is equal, PV is nRT, okay? So we want to write this whole thing in terms of in terms of volume. So what we'll do is nRT by V times dV will be integrated from VA to VB, okay? Now, the right hand side, all these three being constants will come out, and this will again become nRT ln VB by VA. Now you see there is a temperature in this side, temperature on that side. Therefore, what happens is, I'm taking this here, therefore your delta S becomes nR ln VB by VA. Okay, so this is the amount of entropy change, and I'll write this equation 56. Now you also know that P1 V1 is equal to P2. So PV is a constant. So this we can also write this in terms of nR ln PA by PB. Okay. So you want to calculate the entropy in terms of volume. If volume is given, you can calculate the amount of entropy change. If pressure is given, you can also calculate the amount of entropy change. Okay. This is for a reversible isothermal process. Okay. Now, let's move to an isochoric process. Okay. Okay. Now let's go to a reversible isochoric process. What's an isochoric process? In which the volume is constant, so there is no change in the volume. Now we have TE, I'll just write this, dE is TdS minus PdV. Now since PdV is 0, the equation now becomes dE becomes equal to TdS. Now you want to calculate the amount of change in the entropy. So you want to take this T to the other side. Now please remember that you can write E. So remember what we have for CV. So this was dE by dt at constant volume. So basically dE is CV dt, right? So you can write this as CV dt, right? So I write this as CV dt. You can write an n for an n number of moles. This comes to this side, the T comes here, and this is T ds. So you integrate the ds, this becomes delta S, this becomes n CV ln and CV. Now this becomes this. Okay. Now I am not going any further from this because now you know that CV can be defined as a function of temperatures. Now CV can be expressed as a polynomial function of T. For in that case, you'll have to substitute the polynomial of CV that is in the terms of T, and then calculate this whole integral. But for now, we cannot assume that CV is a constant, therefore we cannot take this out because CV is actually dependent on the temperature. So whatever that dependence is, you just bring in that dependence and you then do the calculations, do the integration, and then this becomes the amount of entropy change, equation 58. And now you see we have not taken any ideal gas assumptions or anything like that. So this equation will be valid for all types of materials, be it solid, liquid or gas. Okay, so this equation will take care of that.